So when we talked about the programs where two or more processes are going to communicate with each other via a shared memory or shared data structure, shared file, even we used pipes. Now, what happens if both of them, one or more processes, access the shared data at the same time? Now, what are the code that we wrote? Actually, we never had an access to the shared data at the same time. Either one child is accessing or other child is going to do so. So what happens if both of them are going to access it same time? Now there is a concept, something called as the race condition. Now race condition occurs when two or more processes, now when I say process, they may be threads, access the shared data at the same time. And the final result depends on the order in which they execute. And then it's called a race because who will win the first. The outcome depends on who wins the race. And like which process or which thread accesses or modifies the data first. So let us imagine like if two people are writing on the same whiteboard at the same time, now without talking to each other. Now if they write in the same spot, the message gets mixed up or lost. And if only one writes at a time, things work very fine. And this is called as race condition. So to understand this, we are going to make use of one particular code. Like we will understand this via a simple code. Okay, where we will be talking mainly about how exactly this race condition problems can be solved. Fine, so let us work out. Now here we would be using two system calls. Okay, say for example, if I write, sorry, mmap. Now we are going to make use of both of them, mmap and unmap. Map or unmap files or devices into the memory. Now here, like what exactly we'll be doing is we'll simply allocate shared memory. Okay, which like for example, when we use say malloc, we allocate the memory, and this memory would be shared between processes. So map a file into a memory for faster IO instead of working in different way. The basic syntax is like here you are going to make use of address. This is starting address. Okay, for map. Then the size, size of memory to map. Then memory protection, like for example, if you want some control on read, write, or execute, correct? Then sometimes you may make use of behavior flag, whether they are shared, private, or anonymous. Further, we will make use of file descriptor if at all we are mapping a file. Otherwise, we will keep it -1 for anonymous. And like offset may be added, depend like if we are using file. Usually this would be 0 if we are not using a file. When like we would be using this mmap function. Okay. Now similarly, there is a function called munmap. Here unmaps the like this unmap function munmap function unmaps memory that was previously mapped by mmap. Now here there are two parameters. Like for example, if I see here address of memory to unmap, what are the value that was written by mmap would be added there, and length like size of memory to unmap, same as we passed with mmap. Like whatever we passed it here, same thing would be writing here. So I'm using this particular function. Okay, this would be used for cleaning the shared memory, and like which can help us to prevent memory leaks at all if they are there. Fine. So let us start writing the code. Now here idea to write this code is to know like whenever we are trying to make use of shared memory, okay, which exactly is doing what? Like it is going to use a counter, say shared counter, each child. Now what we want is they are going to access that same thing. Now what happens if both childs are done? Like they are incrementing the counter. Let us say we are having a counter added there. They are incrementing that counter. Now what is the value showed towards the end? Which process finishes first? Okay, so let us try to work out the code. So to do so, like what we would be doing is we will write, say, because we want no synchronization. So synchronization dot c. So we will include the header files, hash include st.sh. Then further, like we have to add unistd.h. Then as we want that parent-child relationship, that's why we'll include c/h. And then we want mmap. So if we save this and if we try to write mmap, so you will see that this file we have to add memory manager kind of thing, right? So we have to add this file there in our code. So hash include sys/mman dot h. Okay. Now further, what we will be doing is we will write the code in main. Now what we will do, we will create one counter. So in this counter, we'll create a shared memory using the mmap function. So let us say we can write it there only. So counter is equal to mmap. Now, as an a parameter perspective, what we saw was like with respect to the say call mmap, the first parameter is address. So we are not sure. So let us add null. Okay. Then we want size of integer there because we are creating this as an a counter. This is length. Okay. Address we are not specifying. Now protection. So let us say we want to protect it. Protect read, protect write. We want it to be anonymous and shared. So map shared. Okay, these are the standard variables, constant parameters, or you can say flags that are used. Map anonymous. Fine. Okay. Then we have to add -1 and 0 as per the definition. We want file descriptor and offset. So -1 because we don't want to write into the file, and offset is 0. Fine. Now what we'll do is we will initialize that counter to 0. So we created a memory map, okay, or we created shared memory. This counter would be acting as now shared memory. Now we will create now the processes. So PID underscore T PID1, comma PID2. Okay, as a structure perspective. So we'll write PID1 is equal to fork. So we have to add semicolon here. Okay, we have to add semicolon here. then PID2, this PID2. So now we are creating child, correct? So if PID1 is equal to 0, okay. Now in the process, we'll use for loop and we'll try to increment that counter some n number of times. Okay, so like if I say, for example, write integer I for loop, int I is equal to 0, I less than 1, 2, 3, 4, 5, 6, 7, 8. Say for example. So we are starting from 0. So actually we should get this number or less somewhat equal to this number. Correct? So I plus plus. And we will increment the counter here. Counter plus plus. Okay, this would be for the inside the if we are writing this for child one. Fine. Now this is for if, then once done, it should exit from that child. Correct. So this is meant for process one. Fine. Now further, like if you see here, this would be used inside the for. Okay, then exit would be used. So we will add here bracket, which I missed to add. And then this is inside this. Like once it is done, it should terminate. Okay. Else, now it should be turn off PID2. Else, curly bracket, PID2 is equal to fork. Now if PID2 is equal to 0, okay, then we will execute the similar kind of code. So let me copy this from here. We'll add it here. Fine. Okay, this is for that counter plus plus again. And then we are exiting from that loop. This is for else. Okay, and then as we are using parents, parent-child process, so we'll wait for children to finish, both the children to finish. So that's why wait system call. Now, depending upon the execution of the processes, we will see that like one of the process would be ending. So when one process finishes, we'll try to display it, like what is the final value of counter, because it is shared. So they are going to manipulate ultimately the shared memory. Final counter value is %d. Let us add a slash n, and then we'll display counter value. Fine. And then simply because we mapped it, so we have to unmap. Unmap what was the address? So we mapped the return value in counter and then size of int. Because counter was the return value for memory map. So that's why we are writing that address in unmap. Munmap and then simply return 0. Curly bracket. Now let us save. Like if errors are there, we'll try to correct it. Fine. Okay. GCC. No synchronization.c dash m13. Okay, we'll try to okay. We wrote exit 0. Warnings are there. So one variable counter, it is giving error to counter. So let us see what is the problem. We'll try to correct it. So we took counter capital C. So this variable should be counter, 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 and let us try compile again. And okay, so exit. So let us see. So we are using exit. So we have to include stdlib. And so let us see even whether we have used main. Yeah, this is the problem. Now I think it is done. So if we execute, now see the counter values. Now both the childs are running. So we will check it here. So we'll write here es dash ejh grep a dot out. Right now nothing. So when this executes, you can see two children are running. Correct. So now the values are different. One can definitely see here what is the change because they are not working in synchronized mechanism. The values should have been similar, but they are different. So we'll try to make small change in the code so as to see exactly the values. We'll remove 1 0 from here and let us see. Still you will see like the values are different because they are not working in synchronized mechanism. Correct? The values are completely different. Fine. Suppose like if we make modification in the code again, we'll make modify here. So we are having 1 2 3 1 2 3 4 5 6 7. We'll check it here there 1 2 3 4 5 6 7. So we'll remove 1. Let us see take the value. Both the cases will make modification. Now execute. You can see because both of them are going to access the same memory, which is shared memory, but still we are seeing the problem there. Correct? Now what we will do is we'll try to make different things here. Like one of the code is working with some value, another one will try to make correction here. So let us take this to be small. This one of the process will be finishing fast. Correct? So let us execute gcc dash m32 no synchronization. Correct? Now we'll have this ready here. Let us see like whether are we going to get now. Yeah, you can see now. Sometimes it is showing correct output, but other time it is showing some different value. You can check it like here we got different, here we got similar, 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 again different, then again similar, similar, what we are expecting as an a counter perspective. So when we execute this, so it is very fast rather right now because we are having those process to be different. Which process wins? It depends on the execution pattern. So let us say like instead of sleep, okay, instead of that exit, we'll add here sleep. Similarly here, we'll add sleep. We'll add different sleep there. So this will take bigger. Okay, and this one will take smaller because let us see which one works well. Because already the process is over, correct? So because it is sleeping, now you can see two children's, that other one is out, correct? Now if I try to, other one is taking time, correct? Because it is working, because we added sleep there. Now you can see the counter value, which one is winning the race, correct? Again, let us try two processes. Let us see which finishes first. So actually this 2.8 ended first, but 2.9 is displaying the value. So we will add it their process ID so that we can exactly see which process is providing us the output. So here we will add this printf here only. PID is equal to %d, and then we'll display get PID. Fine. We'll copy this and we'll add it here too. Because we earlier wrote exit, so the process was terminating. It was not printing it uh, more than once. Now, as we haven't rather what you can call it as added their exit, so that's why it is printing it 3 times. The reason being in two children's and as well as in one parent. So we'll try to write that here too. Fine. So let us execute this. Compile, execute. Now you will see 8877. You can see the difference. Who got the chance? 79 is printing this. 80 is printing this. Correct? 78 is printing this. Now you can see like if you see 84, 83, 82. So 82 is a parent. 83 and 84 are children's. 84 finished first. So the value that was used by it is this one. Correct? Now if I try to write that exit instead of sleep, then it will print only once. Correct? Because process terminating, it is not displaying any other thing. Now execute. The process ID is definitely changing. Now you can see the difference in the value. Correct? Whatever the value it was printing. There is a difference, huge difference. And that is the reason why we say that like we will require some mechanism to make use of synchronization, and race condition is occurring there. And that is the reason why we are seeing different values displayed there.